Welcome to Book Bites, a book club podcast for developers. We're going through 7 languages in 7 weeks by Bruce Tate. And this week we're finally in the last chapter, which is Haskell. And I'm super excited not only to talk about Haskell, but to be done with this book.
Yeah,
I really enjoyed this book, but it did get harder as we went through it.
Yeah, it's been quite a journey going through all of it and just like having to switch it up over and over and over. But I guess that's the whole premise of the book, is doing it and like time boxing yourself to only a certain amount of time on a given language though.
Yeah. I didn't get to all the exercises this time. I did type in some of the things as I went through the book, and I did one of the exercises.
Mm-hmm.
So I spent about 4 hours on this week, which is not much time at all. And it just, not only is it harder language than the other weeks, I think Closure and Erlang were the hardest for me, but I don't know, I just kind of got tired of learning so many languages in a short amount of time. Like just when you start to get comfortable with one, then it's like, all right, time to learn another one.
Yeah, I get what you're saying. Like you didn't have enough time to completely get cozy with any one language, but and then Haskell is a heavy one to land on. I mean, it makes sense like why it's on the end. I mean, you can definitely see like the kind of arc that we went through in the process of the book, from like very object oriented with Ruby at the beginning, and then
IO is kind of object oriented, but it's prototypal.
Right, and then Prologue is just
weird.
Where it really started to depart. Yeah,
but I want to go back to Prologue because I did get that book about adventure in Prologue, and I want to go through that and see how that works. Prologue is just weird and fun.
Yeah, it is. I mean, I think I would put it in a similar realm to that of like of Haskell, and that it's a pretty big departure from what you commonly do, like what I commonly do,
right?
What you commonly do, and so that's kind of the cool part of Prologue. That's a nice part of Haskell. So yeah, let's talk about Haskell. Like, have you ever done any of it in the past?
No, I'd never done any of it. What about you?
I do have a history of having done it in the past, a couple of times. I've had a few starts and stops with it, and it kind of feels like that is almost the way that the language could be best approached. Is like you get into it for a bit,
for a little bit, and then stop.
Right, because it I mean, it can definitely be daunting, like being a pure functional language. I mean, like even just like getting into the description of what that is can be like, whoa, like pure, like what do you mean by that? And
right,
you're like, oh well, I mean, pure means side effect free, which is really easy to describe in like the small case.
But how do you do stuff?
Right. Yeah. So like, because it's super easy when doing, like, say I want to make a number that or a function that adds two things together and then multiplies that by 2.
Yeah.
That's easy to do. And I mean, you create a function that's got 2 arguments, and then it does that process. Like there's no outside state influencing it. But at the same time, there is also no outside state that gets affected. And so like you're faced with the question of like, okay, you created this function and it can perform that operation, but like given there's no actual output of it or like true side effect from it, did you do anything at all? Or should, like,
if a function falls in a forest,
right? Like, like if you call a function but never use it, like if you call a pure function but never use its return value, like
you don't display any, like,
did it ever get called
UI or something?
Right. Like, I mean, because like UI itself, like that is literally state in one.
You have to be able to change it at some point.
Right. And so I think my first entry into doing Haskell programming was going through and doing like Project Euler stuff. I have a project on GitHub from a while ago that I did. I think it was like the first 10 Project Eulers in Haskell. And it works out really well for that because, I mean, the state is really pushed to the edges in that like the only way that you actually see the output is is just by like calling it through GHCI, the REPL for like the most common REPL for Haskell. And so like you're relying on that to like print the output of it
Yeah.
and call the functions. So like that's where the state lives, but not in the program itself. And so like it worked out pretty well for those cases because those are very math oriented type of things. And so you don't need to have a side effect.
Mm-hmm.
You just need like a single numeric output.
Yeah. And this chapter put it well. It said Haskell makes hard things easy and it makes easy things hard.
Yeah.
Like printing something to the screen is something easy that it makes hard.
Yes. I would agree on that. Whereas like, I mean, I have this one Project Euler, I think it's like problem number 5. And it is like, what is the smallest positive number that's evenly divisible by all the numbers from 1 to 20? And I mean, it is like a one-liner that calls like one function and uses like it uses fold, which is like reduce, and like you may hear it reduce in other languages, but and then there's a function LCM for lowest common multiple, and then you just give it that list, and like that's it.
It has lowest common multiple built in.
Yeah.
Wow.
So like that implementation was awesome because it was just like single line, like really can't do. I mean, it's very clear, very short, but yeah, much like you said, like printing out a line, all of a sudden you're into this realm of side effects, and like while it's pure, it's just a totally different approach. So yeah, I like that.
Well,
that start.
Let's get into the introduction. It says that Haskell was born in 1990, and it was created by committee, which is kind of amazing.
Yeah,
There was this conference called Functional Programming Languages and Computer Architecture that got together and made it. It was just built from the ground up. They wanted something that was a pure functional language, so they combined ideas from the best functional languages at the time. They had a special emphasis on lazy processing, and it has strong static typing, which is mostly inferred.
Mm-hmm. Yeah, it did make me stop and think when it faced me with the question of imagine the language that you use or is like your favorite language, and very likely it was designed by a single individual that shaped out things like
at least at the beginning.
Right, like it's not that nobody else has ever contributed to those things, but I mean you think about, I don't know, just kind of stepping backwards, like we had Clojure previously, and I mean that was built on Rich Hickey's hammock time was kind of his idea, where he spent like 4 years like thinking about the language and building it up, while meanwhile burning through all of his retirement savings.
Wow.
That's how it came to be. And like Erlang, I think that one may have been like 2 individuals, but I know like Joe Armstrong was like the like key person in creating that, because he won't. I mean the book talks about it with him wanting to just go and extend Prolog.
Mm-hmm.
And I don't know, and just moving backwards, like Scala, there's like Martin Ordersky, and yeah, so many of them. There's very much a name that's strongly attached to that, and with Haskell, like at least for me, like nothing pops immediately to mind. So that was kind of cool to hear that it is a successful committee language.
Yeah, and in this chapter, he interviews 2 of the people that were on the committee. So that was kind of cool that he got to interview more than one person. Oh, and I forgot to mention, he compares each language to a movie character, right? So this one is Spock. Very logical. But then when you get into more of the advanced stuff, there's like this mind meld that happens.
Yeah. Like logical. I mean, you think like, I guess, Prolog also being logical, which I think was Rain Man.
Yeah.
But I mean, also Haskell being really strong on its principles as well.
Very principled, yeah.
You have to fall within its bounds because of the purity type of things. Whereas even in Prolog, I remember like writing the socket server, and that was very like that wound up being imperative-ish inside of Prolog, even though it's a logic language. Or so.
Mm-hmm. Yeah, some other things about it. It has a special emphasis on lazy processing, which is pretty cool. And did I already say that?
I don't know if you had actually brought that up, but
I think that you can make ranges that are infinite ranges, and it's just not going to evaluate it until you do something else with it usually. And if you try to print out an infinite list, then it's just going to keep printing forever. But you can take like the first 5 or something.
Yeah, and it is super lazy. I think I've mentioned it to you before. Once wrote a blog post about Haskell and like tail call optimization.
Yeah,
and was completely wrong in the way that I had thought about it, and that like while in a lot of languages, even things like adding like a plus b, like if you're doing like a Fibonacci sequence, like you're adding a like two numbers together.
mm-hmm.
Well, even with that, like a lot of languages will like immediately evaluate that, but even that will actually get built up by Haskell is something that's not evaluated in a storage that is called the thunk.
Thunk.
Yes, yeah, you can go and find an article about it. I think just on like Haskell's docs, but it is kind of like you can think of it kind of like the stack, but it's not the call stack, but instead it is like a separate piece of memory for like unevaluated things. Because if it doesn't need to evaluate it, it will not.
Yeah.
Until it is truly needed.
It's like a lazy kid or something. Like, do your chores. No, I don't need to yet. Do your chores.
Right.
Fine.
Right. Like do your chores. Like we're going to the ice cream store if you do your chores, and then like
yeah,
all of a sudden it's happening. So right. Or maybe it's even like clean your room, and
mm-hmm.
the room doesn't get cleaned until you go to open the door, kind of thing. Like
oh yeah. It also has list comprehensions like we saw in Closure and Erlang, and this is got to be one of my favorite things I've learned from this book. And I want every language I use to now have list comprehensions.
Haskell was actually the first place that I was exposed to them, and yeah, they are definitely like a powerful syntactic construct, right? I mean, you can have like combinatorial things with multiple lists, as well as being able to go and filter them and have pretty clean syntax for handling that.
Yeah, it's pretty cool. Okay, so in day 1 we saw, hey, it's pure functional. Learn some basic expressions, some simple data types, nothing crazy. We saw also that you can't mutate variables, and then it showed how to solve a problem using recursion, and then also pattern matching and guards.
Yes,
which we've seen before.
Mm-hmm.
What were we going to say?
I was going to say that was yet another thing that was my first exposure to was in Haskell, and like after having done it, that is another thing that I feel like I want in languages that I work in, and I kind of yearn for it in like doing JavaScript type stuff.
Yeah, it is pretty cool. The pattern matching and guards, it's like you're writing the same function multiple times, but you're like, okay, here's the base case. If the parameter coming as an empty list, then return 0 or whatever. And so that's just a super simple definition if it matches that parameter.
One particularly nice thing that Haskell has going for it too is that its pattern matching is exhaustive, in that like if you try and pattern match against, say, a list, and say you match against an empty list, and you match against a list that has like one item, but then you don't add another implementation in there. the compiler will actually not allow you to compile that because you've been non-exhaustive. Like you haven't accommodated the case that there are more than one in that list.
Nice.
And
yeah, so even if you're like, oh, that will never happen, I'm smarter than the compiler, you
right.
still have to write it.
Yes, like
You have to cover everything.
Right. And more common than while it is true that may never happen case exists, more likely is you as a human are fallible and are forgetting some particular case.
Yeah.
And there is a way to say like you can match anything, which is just by like binding to a variable and then not using it. Or if you want to not have a warning, if you just name that variable like underscore, then it like that's a way of indicating like I don't care about what this value is, but
yeah,
if I get anything else, basically, then do this behavior.
Gotcha.
Mm-hmm.
And then what are guards?
So I mean, a guard is a way of saying like this needs to be true in order for this function to get evaluated or for this to match. I think we did something similar in Erlang as well, where you can say like this function applies in the case that the number coming in is odd. Otherwise, move on to the next implementation.
Gotcha. Yeah. And then we also learned about tuples.
Yeah.
Building lists, list comprehensions, ranges, and lazy sequences.
Is it in day 2 that we got on to currying and partial application?
Yeah.
Okay.
Yeah, day 2 starts with higher order functions, and then it talks about the list libraries, common things like map and fold. There's fold left and fold right.
Yeah.
There's another one that I was not familiar with. There was zip and zip with, but let's see. I forgot what zip does.
So zip is for going over like 2 lists at the same time. Like say you have 2 lists of the same length and you want to iterate over them together. That is what it's useful for.
Does it right, it iterates over them, but it matches the indexes of each one. It's not like coming up with every possible combination or something.
Right.
That's what a list comprehension would be for.
It's index, like if you're iterating over 2 lists at the same time, it's like index 0 of list 1 and index 0 of list 2.
Yeah.
And then you get those.
And then zip with lets you add a function to that or something.
Yeah. So it says like when those things are zipped together, like what you produce with it. I guess I would say so. At least that's my understanding. So like you could go and zip with and like multiply. So if you wanted to multiply both lists that you're zipping together.
Yeah. Cool. Yeah. And then it gets into partially applied functions and currying.
Yeah. When I first encountered partially applied and functions and currying, I didn't quite understand the difference because they are kind of related concepts into function arguments, but they are definitely different things. So
I feel like you need currying in order to create a partially applied function.
I guess you don't need to have it, but currying plays into it really well. Like it makes partial application really simple in that like currying, if you have a function in Haskell that you define, say it's the add function because I don't know, you want to create your own and
you want to reinvent the wheel.
Right. Yes, totally reinvent it and not use a plus for some reason. Then if you were to go and say add takes in x, y, and then equals x plus y using the symbol, that while like you can go and you write it that way in Haskell where it looks like this function is taking 2 arguments. In fact, like the typing of it, if you even go and look at it, is you have you've created a function that it is a function that takes a number that returns a function that takes a number that ultimately returns a number.
Yeah.
And so that is currying is turning like a function that has like n arguments and instead creates n functions that takes a single argument.
Yeah, and so because of that, if you use that function and pass in only one argument,
Mm-hmm.
then you get a function in return that takes in minus
Right.
one arguments. So
Yes.
like with add, you could call add 2,
Mm-hmm.
and now you've got a function that adds 2 to whatever you pass it.
Exactly.
And I like the example of multiplying a little bit better, because if you have a multiply function, you can call multiply passing in 2, and all of a sudden you've got a function that doubles.
Right. Or you have triple with
Or triple
3.
if you do multiply 3.
Yeah. And so, I mean, and the reason that plays well into partial application is that partial application is kind of like you said, being able to pass one or more arguments into a function, but like less than n, less than the number of arguments, and being able to get a function back with the remainder of arguments that you can call it with.
Yeah, and I think like at first when you hear about this concept, you're like, well, why would I want to do that? And I can't think of very many examples, but the double and triple that helps me realize that it can be really useful.
Right. I mean, I would say a common case is, imagine you wanted to create a function that was mapping over something, that was filtering over a list, and you wanted just like all of the odds out of it.
Yep.
So you could go and create you create one function that's like odd, like is odd or something like that, and checks. Using I don't know, check if it's mod 0, like mod 0, and then from there you could actually say like odds that takes in a list of things, and you would just say that it's equal to filter is odd. So like you go and partially apply something like filter, and
right, you partially apply filter by passing in the function that's going to filter with, but not the list.
Yes.
Okay.
And so by doing that, now you have this reusable odds function, which, I mean, just for odd isn't the most likely real world thing.
Yeah, it might be like straight A students or something.
No, right. But I mean, what it allows you to do is use like, I don't know. I find that it's more useful in the case of like a higher order function, a function that receives a function like map or filter or something else, where you want to fill out part of the implementation, but you don't want to do it with the specific data.
Yeah.
And that's actually one thing that if you use JavaScript, you've likely encountered Lodash.
Yeah.
I mean, you may have used it once or twice, and there's actually I think it's a blog post, and I think there was a talk to go along with it called Lodash, You're Doing It Wrong. And if you think about like Lodash in JavaScript, I mean, if you say you were to call the function map in Lodash, your first argument, or the first argument to map, is always the collection, and then the next argument is like the iterator thing. And so if you were to go and want to try and partially apply that, there's not a way that you can do it, because it's taking the most specific argument first, which is like wrong for partial application purposes or functional programming purposes, where you want to apply it, but apply like what the iterator is, but not the specific thing. And it is actually something that's influenced the way that I look at my function signatures when I create them. Is I'm now driven to say like, okay, what is the most specific thing? That should be the last argument.
Gotcha. Yeah. I mean, I don't know how much that matters in JavaScript, since you can't partially apply or curry anyway.
I mean, you can, like, I mean, there's like function.bind.
Ah, okay.
I mean, you have to pass like a null this context to it, but yes, like that is something that's there, and If you also are using something like Lambda JS, just kind of a more functional oriented Lodash like thing, then functions like that apply really well into it. So, I mean, there is value in it, but it is true. Like because the language is not built around the idea of partial application, like it's less valuable there.
Yeah.
But yeah.
So what did you think about this section about function composition? Because it was talking about how a lot of times in Haskell you're reading from inside the parentheses from the inner to the outer, and that can
Mm-hmm.
be kind of backwards or hard to read. And sometimes you just want to see it like in order from left to right. So there's this way to do function composition where it's stringing functions together instead of nesting them.
I mean, it kind of made me think of the like what is it like the fog thing from math in school, where like if you had like f, and it wasn't like a dot, but it was similar to it, like it was like a circle,
Mm.
and so like you would apply g and then f to whatever the result of that was.
Yeah, that sounds familiar. It's
Yeah,
been a long
I mean,
time.
yeah, I don't remember exactly like what that symbol was called, but that's what comes to mind for me
There's probably some
with
math
that.
people that are like yelling at us.
Uh, I mean, this whole whole part is like whole chapter. I'm probably getting things incorrect because I do feel like Haskell is just like this super deep pool. Like I mean, the things that are touched on in these 3 days that it puts you through are just the surface of really what is going on in the language. Like there's so much unknowns with so many unknowns. I mean that like they even talk about it during the interview, is that Haskell is really like a laboratory to go and try out all sorts of things too. And I mean, I don't know. I've seen um, articles about like Haskell having like the beginnings of dependent types and stuff, and like that's something that I don't even understand. Like the simplest concepts of that. Like I mean, its type system already is quite complex, but apparently you can have it do even greater guarantees about the types within your system, and like the data that's flowing through your system.
Yeah, and
Which,
apparently you can do recursive type definitions,
yeah,
which I just don't even understand. I don't know if it
so
touched on that or not, but it mentioned you can do it.
I don't know. I thought maybe it touched on it in there, and that like I mean you can have like a think of like a tree. Like you can have a node in it, or you can have kind of an end. Like so, you can either have like a node or a leaf, but like every
Yeah.
tree can contain another tree.
Oh yeah, yeah.
Yeah.
That's right. So anyway, yeah, the function composition, it's a dot. You put a dot between the different function names, and then it
Mm-hmm.
will use them from left to right.
Yeah. And
I think that's just kind of a matter of preference.
I mean, that is another thing that's like in, um, I mean, bringing it back to JavaScript for you with Lodash, you may have seen like the pipe function that's available that takes a list of functions and then applies them in sequence.
Oh yeah. Yep.
So similar thing, but there's a syntax for it.
So the next interview, we didn't talk about the first one, but the next interview is Simon Peyton Jones.
Mm-hmm.
It was interesting to me because it said Haskell is enjoying a substantial upsurge in popularity, like 20 years after it was designed.
Yeah.
And that's unusual because usually languages succeed or fail in the first few years. But
Yeah. I
I don't
mean,
know, he's like, well, Haskell has a principled adherence to purity and the absence of side effects. So that's super unfamiliar, and you have to be very disciplined. That's kind of prevented it from becoming a mainstream language.
mm-hmm.
But maybe over time, those benefits are becoming apparent to people.
Yeah. I mean, there are things that while even when it's not adopted all over the place, it does have really strong influences on languages. I mean, having done like Rust, I mean that is one place that I feel like it is like having a really strong type system in this same manner as Haskell's is apparent there, and like it allows you to have like a lot of guarantees when you're writing your program in order to like write more correct software without having to write like as many tests.
Yeah.
Like, I mean, that is the one thing is like, yes, you may have to be jumping through hoops to make the type system happy early on, but like, especially like as you're getting familiar with how the language works, but it's also catching things that you may not consider as a human, or like at like something that may wind up blowing up at runtime later on. And so like it's doing a lot of work for you, and I think that's one of like the key benefits of a type system is like you are having the computer to do work so you don't have to do it so
Right.
much.
Also, the computer is making you do work.
Yeah, I mean, like it is very strict and principled as to what it accepts versus just letting you put in whatever you please, and then hopefully it works.
Yeah.
Like, or hopefully you've written a test for it or something like.
Mm-hmm.
Yeah.
All right. Day 3 is the mind meld. It
Mhm.
covers types, classes, and monads.
Yeah. I would say like before getting into day 3,
Yeah.
you said you did like one of the exercises. Like, which one did you do?
Oh, in day 1, I did the one where you need to reverse a list.
Okay. And tell me about that experience for you. Like, how did you go about that?
It was hard because I feel like it didn't know everything yet, just from what they mentioned in day 1. But I knew immediately that. So I wanted to write a type definition for the function, and I knew it was a list of something going to a list of something, and I didn't know how to write like a generic type. So I was like, okay, well, I'll write it for a list of integers going to a list of integers.
Right.
And then I made one definition that says an empty list equals an empty list.
Mm-hmm.
Yeah, the reverse of an empty list is itself. And then after that, I knew that I needed a pattern match where I take off the head and the tail, and I need the head to be on the end, and then I need to reverse the tail at the beginning. But I didn't know how to combine those two things together. The only thing I knew was like the double colon, but that once for that to work, you need to have a list at the end and one thing at the beginning or something like that.
Yeah.
And so I couldn't figure it out, but then later on I figured out how to use plus plus.
Yep. Yeah, that is kind of confusing thing, or like, I mean, not confusing, but like something that if you don't know about it, like there's it's just not immediately apparent. Like, oh yeah, plus plus, because it's unique to the language, I guess, is kind of the key thing. Like I don't know anything else that uses plus plus in the same way.
Yeah.
So yeah, and that implementation was the same for me too.
Yeah. Day 3.
Yeah, sure. Let's get into day 3. So it was the mind meld, and the day that we touched on, I guess, first types. So like having something beyond like just the built-in types of the language, or is something that we got to exposure to.
So I like the example he used where you make a deck of cards. You make different types for a deck of cards, where you've got a suit that could be, a spade or hearts, or actually that's all he has in the example, but you could do all 4 suits.
Yeah.
And then that reminds me of a union type in TypeScript, where it's like,
Yeah.
it's this or this or this.
Mm-hmm.
And then rank is the same thing. You kind of list out all the different options.
Yeah.
But then a card kind of combines those two things together, where it's a tuple that has the rank and the suit. And then a hand uses card. It's a list of cards.
Mm-hmm. Yeah, I did think it was definitely like a good way of thinking through it. And also, like, I think it's cool that you can use that information as well, like the like types and data, in order to go and like pattern match based off of them as well.
Yeah.
So and that's kind of where like the exhaustive pattern matching that I talked about earlier kind of comes in, where like if you are doing a match and like you're matching against suits, but you only were to say look at spades but nothing else, like you would get told by the compiler, no, like you're not looking for the other suits, so like you have to fill in other implementations one way or another.
Yeah, that's really cool. And then classes, I don't even remember.
So
Because I know it's not like a normal class.
no, it is not. It is more like I mean, in Rust, like they're called like a trait. I mean, it's almost like an interface.
Right.
I think that would be the closest equivalent, is to say like this set of functions has been implemented for this type.
It gets really confusing to me how so many different languages use the same words to mean different things, or they
Right?
use different words to mean kind of the same thing.
Right. I mean, I guess one thing you have to go off of is that like Haskell was written in what was it, 1990?
Yeah.
Was the kickoff, and so I mean, given that I think Java came post that. I think that came like in the 90s.
Right. Well, what about C++?
C plus. Oh yeah, I don't know.
Yeah.
That's fuzzy. So. But yes, like terms that mean something pretty distinct in your mind, programming wise, that are like no, it's not that.
Mm-hmm. It's like
But
you need to erase parts of your brain when you learn a new language, but not all of it.
yeah,
Just some things.
yeah, I do like though that things like in Haskell, that with the classes, like type classes, that they are so generic in cases that it allows you to make really generic types of functions. So for example, like EQ for like equality, like that itself is a type class. And so you can say like this data can be checked if it is equal or not equal to something. And so you can write an implementation of a function against that particular type class.
Right.
Or you can say even something is ORed, where it has like things can be greater than, less than, or equal to each other. So that's like an extension of it. And so everything that implements ordinal or ORed also has to implement EQ. But like it's such like a generic way of doing something, to say like you can call it a sort function, and I can sort anything as long as it is comparable and implements this type class of ORed, rather than having to go and implement it for something specific.
Yeah.
And because I mean, while in other languages, like you can go and do sorting, a lot of times you have to give some sort of function implementation on the spot in order to sort that thing.
Yeah.
So like if you're sorting, say, a I don't know, a list of like Olympic swimmers or something like that, then I mean, in a lot of languages you would have to say like sort, but here's my comparison function, which is like their best time or something. Like it's swimmer.best time is the way that I'm doing that. And you could actually say like the type of Olympic swimmer implements ORed, or ORed is implemented for it, in that best time gets compared. And so like that definition is done elsewhere and across the board.
Like everywhere in your program, you never have to worry about that again.
Right.
Just,
like
just sort.
Yeah, you just sort it, and because there's that
That's cool.
implementation
So
of
it's
it.
like you can wrap up some of your domain logic in the type.
Right. And like it's in the type, but like I mean it's yes. So it's in the type, but it's not necessarily part of the original implementation of it. Like I mean you can have anything implement any type class, because it's not like a class, say in like Java or something, that like you go and you have particular methods on it. Like type classes are not methods, but more like a group of functions that are implemented for a type.
Yeah.
So yeah. And
What about monads?
what about monads? Yes.
See,
So
he said he ever since he started writing this book, he dreaded writing the section on monads.
yeah, I mean, there's the classic like monads are a monoid in the category of endofunctors.
Of course, yeah. I was about to say that.
Right, and so like that, and I have read like a definition of that goes and clarifies like what that means, and it breaks it down.
I thought you were going to say that the thing about monads is if you understand monads, you can't explain monads. Is that what it is?
I think that is another one. Like there are so many approaches to it. I mean, there are monads are like burritos. Like that is one to look up. I think there's even like a JavaScript monad library called Burrito.js for just that purpose. And
Nice.
and for me, I still am not like capable of explaining it in like a nice, concise way. Like I would say like I don't totally grok it as a whole.
Yeah.
And
All right,
so like,
we're done then.
right, here we go. Thanks for listening. So that is one thing that I feel like I wish Bruce Tate didn't say, is that that they were, I don't know, kind of, he came to understand that they're pretty easy. Yeah, like he said, I've learned, like after some study, I've learned that the concepts are not all that difficult. And I think I don't know if that was necessarily the best approach. Maybe not all that difficult for him, but like
Yeah. I liked one thing he said though, that he said you'll probably need to wade through several examples from many different sources. Wait,
yes,
wouldn't that be many examples? To come to an understanding of what monads can do for you.
yeah, and I would agree with that, because like there are different, like there are tons and tons of approaches to it. And I think one thing that helped me understand a bit more was, instead of looking at the definition of monad immediately, it was actually looking up on the Haskell wiki their definition of a monoid, which is like yet another scary term.
Mm-hmm.
But in fact, like while it is an intimidating term that's brand new, it's also like a well understood term, or like it has a strongly defined meaning. Much like, I mean, we in JavaScript, like there are words like closures, which like at first like you hear that and you're like, wait, what? I'm closing something, but like it has nothing to do with closing. but like after you learn it, it's like, oh, okay, I know what that means. And so for like a monoid, it is a structure that happens to go and implement a specific interface that obeys certain laws. Like there are a few laws that apply to it, or like rules that thing adheres to in order to be classified as a monoid. And so like for like looking at a monoid in particular, you can think of it as a type that has a kind of base case. So like think of, I think they give the example of like a sum monoid. So think of a data type in Haskell, like a type that can hold some value,
mm-hmm.
and call it sum.
Yeah, SOME.
And what? No, actually SUM, like addition sum.
Oh, okay.
And the base case of it, or like the pure case of it, happens to be like what gives you identity in a sum. So like when you're adding two numbers, like the base case is 0, or like
Plus,
identity case is 0.
plus
Like
0,
if you,
yeah.
right. And so like there always has to be something that represents the identity case, and then there is also what is known as concat. And so if you concat two sums, like so if you concat there's a function that's called concat, and if you concat the sum of 1 and sum 3, like you're going to get sum 4. Like that's the way that it works. So like sum A and sum B, you get a sum of A plus B.
Yeah.
It is, and so you have both of those function implementations that need to be met, as well as the law that the sum of A plus the like identity case or base case like always gives you back the sum of A. Like that's your law. And I think there are a couple of other ones as well that kind of work that logic in another direction. But by doing that, you can see like, okay, you could do the same thing with like multiply, right? Which, I mean, that's not like a real world case, but you can expand upon that to something like list. So like think of an array in JavaScript, or I mean a list in Haskell.
Yeah.
Like, I mean, if you think of the base case for it, like what is the base case of a list?
An empty list.
An empty list, right? And so if you can cat a list of 1, 2, 3 with an empty list, you're gonna keep getting a list of 1, 2, 3.
Yeah.
Like that's not going to change. Or if you can cat 2 lists, you're gonna get, if you have 1, 2, 3, and 4, 5, 6. If you can cat both of those, like you're gonna get 1 through 6.
Yeah.
And just kind of moving on, like from understanding that, then you have also like another thing that monads adhere to is the functor type class.
Functor.
Yes. Functor is something that implements the function of fmap, or just think of it as map.
Map, okay.
And like in JavaScript, you can think of it there. Like say you have a list of 1, 2, and 3, and then you call map on it, and you inside the map function you give it times 2. Like you're gonna get like 2, 4, 6, right?
Yep.
But the important thing with it is that like you're saying like apply this function to the contents of it, and I don't care how many times you apply that function. Like it can get called 1 time, it can get called 0 times, it can get called 100 times. It doesn't really matter. But the important thing is that you always wind up getting a list back, or that you always get something of the same type back.
Okay.
And so map always gives you, like, it takes a functor of A and some function to apply to it, and then you wind up getting back a function of A, or I guess you get back a functor of, like, you get functor, a function, and then you get a functor back out of it. Like you don't ever change types there, because you're not you're not extracting the contents of it out, but instead you're like working within it.
Okay. Yeah.
And I don't know, that like knowing both of those, because monads need to adhere to those, I think that helped me understand it a little bit more. I'll give you a link to it so you can look at it, because me just explaining it to you verbally can only do so much. And like Bruce Tate says, like getting multiple exposures to it kind of helps you wrap your head around it a bit more.
Yeah. And I think what's important here with Haskell is that monads are how you do side effects. You're not actually doing side effects, but you're somehow using monads to return a side effect, which is later executed.
Right. Yeah, you're like describing what needs to happen, or like what do you want it to do, and Haskell, being lazy, may still never apply that thing.
It's just so funny.
Yeah, and I actually, I don't know how much the drunken pirate example really nailed it for me.
Right. What was the drunken pirate example again?
So that's
right. It has something to do with the pirate's drunk and he's trying to find his treasure, and so he can either stumble or crawl.
Right.
Stumble is 2 steps and crawl is 1 step. Yeah, that example didn't help me much.
Yeah. And I think in turn, probably one that helped out a little bit more was doing like the IO related one, where it calls on getLine, which is like asking for input from the user.
Right. Which is a side effect.
Right. Which is, yeah, definitely a side effect, and working with external state, where like it's not inside the program. It's definitely not known until until runtime, and you could get anything out of that.
Yeah.
But I mean, then what you're
users
saying is
can
like,
do anything.
right?
You never know what a user's going to do.
Yeah, particularly if you have QA taking a look at it.
Yeah.
But so like you could get anything. But what's important is like you're describing kind of at the edges of your application. So like commonly it's inside of like main in your program, or like main, or I mean like if you are say you were doing like a web request type thing, like you are putting that to, I don't know, to like what I like to think of as like the edges or like the boundaries of your application, where like that state comes in. And then ultimately, I mean, you would wind up saying, okay, well, they put in like three, like they put in three because they, or I don't know, yeah, like maybe your application like reverses whatever they put in. I mean, I guess even that example does that, where they go and reverse like what was typed in, where it says your name backwards is whatever it was backwards.
Yeah.
And at that point, like you are once again like using that in a functional manner. Like you're taking that that input from the user and you're just passing it along to some like actual pure function again. And so then you're kind of going through a just like pure like data flow function calls rather than worrying about IO until ultimately you need to print the result back out, and then you're describing that again. So it's like it's one big chain of things that they use that very different operator, that bind operator, where they do greater than equal.
Yeah.
To like take the input of one and pass it to the next and to the next, and then the do syntax being like a nicer way to write that in a more imperative fashion.
Yep.
Yeah.
Well, let's wrap up Haskell and then let's wrap up this book.
Yeah, I would say one last thing for Haskell and my chance to play with monads. I didn't go through a bunch of the exercises in part 3, other than the like using the list monad.
Okay.
I think I told you about that after day 1, was using the list monad to solve the states problem from Prolog.
Map coloring problem?
Yeah.
Yeah.
Yeah, where like every boundary, like every state that boundaries another state has to be a different color.
Yeah. And you can only use certain number of colors, maybe?
Right, yeah. So you have like 3 colors, I think. I mean, you can have n number of colors and various states, but I mean, it was given with like a specific set of states and a specific set of colors. And by using the list monad, you're actually able to go and write it in a very like logic-like way, sort of like Prolog, where I was able to say like Alabama is red, blue, or green, and Florida is red, blue, or green, and then a few other states, and then within it there is the list monad happens to implement a function that is called guard, and which can take in true or false as its argument. Like it pattern matches against true or false, and if it is false, then it gives back like empty for the thing, meaning that like it will not add that entry to the list. And so I was able to add a bunch of guards to say like Alabama needs to not match Tennessee, and Alabama needs to not match Mississippi, and list all those rules in the same way that you did inside a Prolog.
Yeah, you're listing all of the states that border each other.
Right. And so I was able to put all the rules in place and then ultimately return only maps that accommodate or that match all of those guards.
Nice.
So it was kind of cool to be able to write it, and it gave a good glimpse into like how expressive Haskell can be.
So it sounds very similar to the Prolog implementation.
Yeah. Yeah. I found an example on the Haskell wiki that talked about logic programming in Haskell, and they
Ah,
gave the example of some other problem, but I was able to shape this one into it, and it was kind of cool and satisfying to write it in that Prolog sort of fashion.
yeah.
And that's kind of it for me on Haskell.
I liked at the end when he wrapped up Haskell, he said that it's the most difficult of the functional languages in the book, for him at least, and also for me, I think. But he said it's also the most rewarding language he learned. And so that's interesting. That if you get past the learning curve, put in the work, it can be really rewarding.
Yeah. And I think, like I mentioned early on, like having it a language that maybe you pick up for a little while and then put back down and then pick up again and learn some more on it. And then, I mean, while you're setting it down, like you're not completely departing from the things that you've learned from using it.
Yeah. Okay, and then to wrap up the book, he goes over all the different programming models, the different concurrency ways of handling concurrency, the different programming constructs, and which languages use each of those things.
Yeah.
So that was pretty interesting. I was before I started this book, I was most familiar with some of the programming models: object oriented, functional, prototype. Didn't know so much about constraint logic programming, which is Prolog.
Mm-hmm.
And then concurrency, I didn't know anything about concurrency before this really, and I really struggled with this concept as we went through the book and was not very interested in that. But I know a little bit more now. I've been exposed to it, and I could come back to it later if and when I need to.
Yeah. And I mean, and concurrency is such a critical thing when it comes to, I guess, various types of processing. I mean, if you are doing lots of front end or JavaScript related stuff, like your approach to it is certainly different. And I mean, concurrency is real inside of JavaScript, but like parallel type stuff is less so. And yeah, the actor approach is still something like that exists in a few of the languages that I have
Yeah.
still not like built out something fully fledged in, but like I can see like the major benefit of it, where you have kind of like these little boxes where you have like safe processing on something, and then like you work on something and you say, all right, I'm done, and I'm handing this off to somebody else to go and continue working on it or
Yeah.
send it back to.
And actors was used in a lot of the languages IO, Erlang, and Scala.
Mm-hmm.
And then it was also interesting that IO went above and beyond the other languages by adding a couple of other ways of doing it with coroutines and futures.
Yeah.
And then Clojure had software transactional memory.
Yep. I mean that, and all of these too have play in other realms. Like I believe that even like Haskell has the same sort of thing for software transactional memory too. Like we just didn't touch in on it,
Yep.
where like you are working on something in parallel and you may potentially go and have to do that operation again. And so long as it is like a pure operation, then it's actually okay to go and do it again or 100 times, because like you're not having any side effects. So that is a legitimate approach to going and dealing with concurrency in a manner where you're not going and locking using like mutexes and semaphores and stuff.
Yeah.
Yeah.
And then you mentioned some of the interesting programming constructs. There's list comprehensions, monads, matching, and unification from Prolog.
Yeah.
Unification was a pretty cool one for me to learn about. And then he talks
like
a little bit about like writing for people who read your code and just learn what other languages have to offer. It can really, whatever language you're working in, it can push that language forward if the people using that language are learning about other languages and then voicing the things that they want to see change going forward in their language.
Yeah. And also even understanding that like some languages are okay not having some of the things that others do. Like they're okay to be like their own unique approach to stuff too.
Yeah.
And be focused on like a particular domain. I mean, things like Prolog, for example, like it is very much its own realm and doesn't solve all the problems. And I mean, like you can, given it's a programming language, like you can solve anything in it, but like it's well suited to certain types of problems, and that is definitely okay.
Yeah. And then he talks about kind of finding your voice with the way you write programs, and learning different languages can help you find your voice. So I thought that was kind of an interesting, cool way to think about it.
Yeah, and I mean, between your voice, like what works for you as a developer too, because
Yeah.
I mean, even like the mental models that we all have for programming, like I mean, some languages, are just really well suited to that. Like if you have some idea of how to solve something in your mind, like some languages may be really well suited to the way that you would express that in code form.
Yeah. So maybe about finding the language that works best for you.
Yeah, right. Yeah. Although that may be harder with some languages than others, but
Yeah.
I mean that's a separate problem to go over. But
so overall, I'm really glad to have gone through this book. It was really challenging at some points.
Yeah.
And it really pushed me, and I didn't get everything out of it that some people might get out of it, but I'm a different programmer, I think, for having gone through it.
And that's, I would say, definitely the intent of going through and trying out new programming languages. I don't remember who said it. Was it like Uncle Bob that said learn a new language every year or something?
Yeah, I don't know.
And I don't know. I will have to double check and look that up. But there was someone who promoted the idea of learning a new language every year, not always with the intention of adopting it like into your normal day to day, but rather as something to expand your approach to writing programs.
Yeah, I think that's a good thing to do. And maybe not one every week for 7 weeks.
Right. Yeah. Definitely. Like it doesn't have to be a weekly language thing. Which I mean, then like this definitely gives you like a direction type thing. Like you've looked at Prolog when you may not have before, and like you said, you wanted to dive in deeper, and maybe like that could be like your language that you learn. Because I don't necessarily call like this what we went through in the book as like learning the language,
Right.
so much as like getting exposed to it.
Right.
But now that like you've seen this, like I mean you're thinking on that subject, like I mean you picked up the book, like what are you going to go and solve with it now?
Mm-hmm. And this book actually had me longing for a conference that's a polyglot conference or something, where you could go to maybe 3 or 4 different short workshops on different languages and get exposed to them.
Yeah. Well,
I thought that would be really, really fun.
Yeah. Interesting thought.
We could have you could have talks that relate to more than one programming language, or just introductions to different programming languages.
I know. I mean, there are some in that vein, like Strangeloop is one that I think of annually. Where I mean, they talk a lot about functional languages, but I mean, it's not particularly tied to only that, but instead, kind of like new concepts to take back and maybe apply to what you do in the daily grind.
Well, yeah, whenever conferences are a thing again, I'll have to look into that one.
Yeah. But yeah, it was a good book. Glad we did it. Glad we're past it, and looking forward to what's to come in the future soon.
Yeah. All right. If you want to follow us on Twitter, I'm on Twitter at AGARRHARR. Jason is at Staten Jason. You can find the show at BookBytes FM on Twitter, or at orbit.fm/BookBytes. You can find show notes and transcripts there. And until next time, see ya.
See ya.